Hello, my name is Fiona Wang, and I'm on the community team at DFINITY Foundation. Today, we have our 10th workshop, and the top topic is Build a DeFi Use Case. We have two speakers with us today, Eero Kelly, Tim Gretler. They are going to kick things off with the workshop, and I will be monitoring the chat for questions. We will save the Q&A until the very end. Please feel free to ask any questions if you have. Without further ado, I'm going to hand it off to the first speaker, Tim. Tim, please feel free to take it away.
Hey, thanks, Fiona. Thanks for the introduction. So let me first share screen over here. So yeah. So hi, welcome to a workshop about our DeFi example dapp. I'm Tim, and I will present this together with Eero. And you maybe already have seen like the published video on YouTube. And in this workshop, we'll go into more details about what we did in our example DeFi app. So first, I want to talk about what we will discuss today. So first, I will do like a high-level intro on DeFi in general and what this means for IC, and also like how it compares to DeFi and other chains. And then I will go through our example DeFi app, how the mechanics work. And yeah, we'll explain you like how the mechanism works. And then Eero will do a small demo and explain you the code, the actual code. So first, just quickly talk about DeFi. So DeFi stands for decentralized finance. And what this means basically is that like your financial interaction, this means your tokens, you do interaction by accessing smart contracts that are decentralized. And this means that there is no like central intermediary that can control your funds. So nobody can like stop you from doing any interactions. And like what is also, it's not only about exchanging tokens, like there are many more financial use cases that you can think of. One popular is, for example, doing lending and borrowing on chain. So you can open like certain positions on tokens. So yeah, so this is like DeFi in general. And so now just I want to put this into context of the IC. So just like first we have a look at what the primitives are that we have here. So like how the IC works is that we have these canisters, and the canister execution is very fast and cheap. And like the IC has this enormous scalability. So, and to have this scalability, the architecture of the IC is asynchronous. So this means that, for example, if you call a canister contract and this canister then calls other canisters, like this will happen asynchronously compared to like other chains. And but on the other hand, for example, I will go into more detail about this asynchrony. But for example, the canister execution is synchronous. So this means like the state of your canister like gets moved by you doing update calls, and this happens in a synchronous fashion. Like either your update call gets added to the state or it doesn't. Another big feature of the IC is that it offers like very cheap storage on chain, and we can think of that this like allows for much more advanced DeFi application, because you're now able to store much more state. And in a lot of DeFi applications, you're limited by the state you can store like on chain. For example, like one concrete example would be having like an order book exchange. So this means that you can place orders, and like these orders get then stored on chain and like matched accordingly. And for example, these order book exchanges are like more capital efficient compared to like what we have on our chains with these automated market makers. And we already see that like this happens, like if you decrease storage cost. For example, you have on Solana, you have Serum. So they also implemented like the order book exchange. And this is only possible because the cost of storage like is magnitudes lower. And on the IC, it's like even lower. And this opens up like a lot of new solutions. So now like this raises the question, like why can't we just like port, and this goes into the asynchrony. So why can't we just port the existing DeFi applications, like the actual implementations, over to the IC? And so the reason for this is like chains with all these chains that we know of with this high total value locked are synchronous. And like synchronous chains have like some advantages because like the synchronicity basically provides you atomicity, but as we know and as we feel is that it doesn't scale well. When this is like, yeah. And with asynchrony, we have like more advanced stuff that we can design. And so just to make this clear again, so like the issue that you have when you want to do asynchronous, when you have with asynchrony, basically when you call other contracts, like the execution happens, and it can happen like even if like the first call doesn't succeed. And this is what doesn't happen on other chains, on synchronous chains. And to go into more detail on this, we will briefly look at like the Uniswep contract. And so just Uniswep, if you don't know it, it's basically one of the main or DeFi application on Ethereum, and it's based on like the automated market maker model. So you don't do actual like direct trades with another person. What happens with automated market makers is that you basically provide liquidity of 2 tokens. And like if you then you then have 2 big pools of tokens, and like these are like according to a price. But just then if you want to exchange token, you put your token in the pool and you get some out of the other pool. And this is how like the exchange works. This is different than what I've explained previously with the order book exchange. And yeah, so let's quickly look at these contracts here. So if you want to, what we will call is like this, we will call the swap tokens functions. And this is in a so-called periphery contract. So periphery contracts like are usually stateless, and this makes them like upgradable, more easily upgradable than like the core contract. And the core contract like just provide you the basics. And these also hold like all the assets. So these are the very important contracts. So if you now look what happens if you want to do a token transfer on Uniswep. So like, let's say you want to exchange like some Ethereum for like another token. What happens then, like you will call this function, and like the first function, the important function that gets executed is that you transfer your tokens to the Uniswep pool. And then this will route you to the core contract. And in the core contract, Uniswep will already like transfer you out your requested amount of tokens. So like the exchange at this point like already happened on the token contracts. And then in a last step, like Uniswep will check like if the actual amounts like fit according to the price. And if it doesn't fit, like here is where the synchrony comes in of the chains. Like all these transactions to the other tokens where you change the funds will be reverted back to the previous state. And this is what this is like the difference to the IC. In the IC, like these executions to the other contracts can happen. And if you then roll back, like in the first contract, like it doesn't roll back like the changes on the tokens. And this is what you have to keep in mind when like you want to develop DeFi applications. That's the reason like why we can one-to-one like port like this application like into Motoko. And it's not about, we can like the idea of Uniswep, like it's portable. It's just about the actual way you are going to implement this. Yeah, so as mentioned, like many of on this synchronous chain, many of these DeFi applications rely on this rollback mechanism that you can roll back like many smart contracts calls. And as we've seen, like in the Uniswep source code, like the actual transfers like happen optimistically. And this is, for example, is not doable in the IC due to this asynchronous model that gives it the scalability. So the big feature is scalability. Yeah, so this is basically, this wraps up like my explanation, like what's this, how we want to implement DeFi. So like now I want to give you the concrete example, like how we developed like our example dapp, and like what would be an approach like to make use of this asynchrony model and still have like good DeFi exchange that is basically not that possible like on other chains. So first, just on a high level view, this is the setup we have. So we have like 4 canisters in our example. We have some token canisters and the ledger canisters, and also like mainly our DEX canister. So first, like we have this DIP20 token standard. So this is basically more or less a port of what we have with the ERC20 standard, and it also provides like the same function with the same naming. And so what tokens are, if you're not familiar, so tokens are basically just a hash map stored in the canister that maps like your basically principal to a certain amount of tokens that you own. It additionally has like some metadata associated with it, and it also provides you with certain functions to interact with the token. So for example, you can have transfer where you can say, I want to transfer some tokens to Eero, or I can check my balance. And like one more function there are like some more, but one that's important, like for our example, is the approve function. So if approve function, I can basically give someone else permission to spend my funds. I can say like the principal ID that like Eero, for example, has ability like to transfer some tokens on my behalf, basically. So next, like the ledger. So the ledger is different. It has a different interface than the DIP. And this means that because it came first, basically. So what the ledger provides you is the ledger has like these notions of sub accounts. So like each user can have multiple sub accounts, and usually you have the default sub accounts where you have ICP. And it also provides you with a much simpler interface. So you can only transfer and check your balance. And like this has some implication, like how we design our mechanism. And I will go into this in the next few slides. So let's look at, for example, a sample token exchange. So this is just the high level setup that we have here. So we have, for example, here I have like Ben that has some ICP, and I have some tokens. And we want to do a trade, basically. And we have the DEX on the right-hand side. And like the colors here like indicate like who controls the funds. So let's start. So I will start by, I want to place basically the sell order. And what I do is I will call the approve function on the token and give the DEX the permission basically take custody of my funds. So what happens now is that the DEX has the ability to take my funds, and the DEX will then, I will call the DEX and say deposit, and he will then basically transfer all the funds to his account in the token, and will also give me the associated balance on the DEX. So this is basically our mechanism here, works by like we give the DEX the custody of our funds. Basically, the DEX has control over all the tokens. And this then we can then make use of the synchronous execution of the canister itself. And we basically just do all the trades on the DEX itself. So next, I'm here and I have now the availability of these funds on the DEX, and I will place, for example, an order here for some ICP. And the next step, like Ben comes around and he has some ICP in his default account. And now for the mechanism to transfer ICP. So yeah, as mentioned, because the interface to ICP is different, like you have to implement a special mechanism for ICP. And there is, for example, also here to mention that you have also, for example, wrapped ICP. And like the idea of having like wrapped tokens is that you provide like a different interface. So for example, you have like on Ethereum, you have wrapped ETH. And like the idea is that you can interact with the ERC20 standard with the wrapped ETH, if I'm correct. So what happens? So Ben first for ICP, if you want to give ICP to ledger to the DEX, because the DEX has the ability to hold ICP. So Ben will call the DEX and ask for a special deposit address. And he gets like this special DEX sub account. And this is for the DEX to know that like he's actually the one that transferred the funds there, like to distinguish if different people send funds. So now Ben will also call the transfer function and transfer this ICP to the deposit address he just received from the DEX. In the next step, it's similar to what we did with DIP. You will call the deposit function on the DEX, and this will notify basically the DEX that I did all the previous steps, and you can now take custody of the funds. And in the case of ICP, the ledger, the DEX will do a new transfer and transfer like all the ICP from this special sub account into his default sub account. And it will also give Ben like the correct ICP balance on the DEX. And now we both have our tokens basically on the DEX. And Ben will go ahead and place his buy order. And the DEX will then, according to some logic, see that these orders match and execute these orders by like internally updating his table. And now basically the trade is complete, and we can even like do like some more trades. So now it's basically, that's the main advantage of our design, because like now all the interactions happen on the DEX, and this makes it pretty easy and efficient and cheap to do these trades. But now like at some point I want to take back my custody of my funds. So I will call the withdraw function, and what the DEX will do, it will basically just do that, call, for example, the actual transfer function on the ledger and give me my funds back according to the internal balance. Yeah. And so this is basically how, for example, a buy order happens in our DEX example. And some things to consider here is that now it's really complicated, and you would think like, how would a user ever do this? But like, if you would have deployed this, you would develop a front end with it, and like through the front end, like you would like collapse, like for example, deposit functions together into one button that the user could press. So you would hide the complexity there, and like only like people that do arbitrage trading would like call the actual functions on the DEX. And another thing to consider is like on the IC, like canisters have a controller, and controller, for example, can upgrade canisters. And this might be not a good idea in the case of a DEX, because like, as mentioned, it holds funds. So to avoid like decentralized control, we can, for example, add like a black hole controller that basically the big contract at the canister becomes immutable. And in the future with the SNS, like this will be like the path to having upgradability for these contracts. And for example, in our example dapp, we separated like all the exchange logic into separate files, because it's like, actually, if you want to implement a correct order book exchange, it gets quite complicated. So like you can go and play around with how the DEX works and like implement like some special functionality. And what's also to mention is that you need to have like an idea. You can take basically fees of these transfers, and you maybe have to manage like that your DEX canister always has some cycles in it. Yeah, so this basically concludes our like high level talk about our example DeFi dapp. And so if you have like any questions about the first part, feel free.
We currently don't have any question from the chat room, but if you guys have any question, you can start to raise your hand or type your questions in the chat room.
No, I'm not the dev of Sonic, so I work at DFINITY. Just so.
Yeah, I think we don't have any further questions so far.
All right, so I can take over from here. Let me just get my screen set up. Hi, so I'll be starting with just a quick demo of the dapp right now. So here we have 2 users set up. This is just in 2 different browser tabs. So one user on the left, one user on the right, and we'll start just by, on the left, we'll just add some of the DIP20 canister. We'll do the same on the right as well. And you can see this is where we've hidden that complexity behind just a single button, just for the user. And then we'll jump back over to the left and we'll just put some ICP as well. And so we can see it's already updating on the balances just because it's pretty quick. And we can now use these balances to open up a new order. So what we'll do is we'll just open an order on the left to exchange some of our ICP for some of the gold DIP20, which is what the user on the right has. And so we haven't implemented any sort of polling, so we do have to refresh on the right. But as soon as we do, you'll see that the order shows up for the user on the right. And if you build your own application, you can add some sort of polling to have this sort of automatic update. We've added this convenient button here that will just open a matching order for the existing order. And then what's happening is that a second order opens up, and then the DEX will automatically resolve it and update the balances of the user. So we can see the user on the right already has some of that ICP, and they've lost some of their gold DIP20. And then another refresh, and we'll see the same thing on the left, that the orders have closed and the balances have updated. Over on the right, we can see that we have, these are some of the DIP20 that we initially submitted to the DEX, and we can just pull those right back out to our own balance. And this ICP is new. This is what we actually traded for, and we can pull that back out too. And again, all the complexity is hidden just on the front end, which is also hosted on the IC. Cool. So that concludes the demo, and I will jump straight to diving into our code. So this lives within our examples repo, so the DFINITY examples repo. And I'm going to go through our Motoko example today. So it lives here at Motoko DeFi. We also have a Rust version of this same DEX implemented here at Rust DeFi. It's the same exchange. It's just implemented in Rust instead of Motoko. So I'll start with just an overview of what our what the structure looks like. So a lot of this is boilerplate. There's some here's our DFX configuration, some Git configuration. I want to point out this architecture MD file. It's just a markdown file that has a lot of what we've talked about just in more detail of the actual architecture of this dapp, and just more in depth of what we're going over today. There's also a really great page on the smartcontracts.org of this dapp, and you can find that just through this link here. So scripts holds a lot of tooling and just helpers for this application, and then test just holds testing scripts. So all of our code actually lives within this source folder. From top to bottom, we've got this DIP20, which is actually Psychedelic's DIP20 implementation, which is the canisters we're using for tokens in this application. And then DeFi dapp holds all of our backend code. So this runs the actual logic of the DEX. Front end holds the front end code. Front end assets is just the assets for the front end. And then these last two, we've got the internet identity and ledger folders. And on mainnet, these are, you'll be able to interact with the actual canisters, but these are just local versions of the WASM blobs that you can just deploy for local testing, so you don't actually have to deploy to mainnet. So I'm mostly going to focus on the backend code today, and as Tim mentioned, we extract a lot of the exchange logic out from the interactions that you actually have to do with other canisters. And we're going to focus on that second part just because the exchange logic can be however you decide to implement it. The important part is how you actually talk with the ledger and these other canisters. So that's what we'll focus on. Here we have just some helpers for interacting with sub accounts on the ledger. And this is how we track provenance of like deposits and stuff right now. And these top three are just utilities. So the sub-account tools, CRC32 and SHA-224 are both just those algorithms implemented. And we just have those because we don't currently have those anywhere in like a common tooling. So we have to pull them into our own repo. So then we have the book, which manages the balances for users. And so this is that internal ledger of who has control of what. Exchange manages the orders and executing them and making the transfers between these users. Types just holds all of the definitions for input and output types and some errors. I want to point out that this DIP interface is the actual interface we use to interact with the DIP20 canisters. And it's just a limited form of the psychedelic DIP20 standard, that just what we use. And so this and some of these types here are just used for interacting with those canisters. Yeah, so again, we're going to focus on just the important parts of interacting with other canisters. So here is where our backend canister is actually defined. You'll notice we use an actor class here, but we don't actually use any parameters. So an actor class is just a way that you can have a canister that has some input variables that can control the initial state. And we did this for two reasons. First, to just match what the Rust canister uses. So we have a common interface between both examples, but also it's just a lot easier to see that if you need to change input parameters to your application, you can control fees. You could take this as a parameter, or if you want to set up anything initial, you can use this as a way to get in. The second thing I want to point out is that, so here is our book, which controls those balances, and then here is our exchange, which is those managing orders. But we also have stable versions of these. And the reason we have this is that currently these structures can't be saved as stable variables. So this is a bit of a workaround that we have just so that we can have upgrades work correctly. I'll jump down to the bottom. We don't recommend that you actually use this in production, but we keep it in just because it's an easy way for you to maintain state between upgrades, so that if you need to fix a little bug, you don't lose your whole state. But really what we're doing here is we're just serializing the those data structures into a form that can be saved as a stable variable, and then saving those instead. So it's just an implementation detail, and we just suggest not to follow this in production. You can grow your memory pretty large if you're doing this, and yeah, you also just might not want to worry about upgrades in case you don't want someone to have control over that. Cool. So now here we are with some of the just interactions with the canister. So things like placing an order, it's really simple, just application logic. We mostly interact with our internal types here. So we do things like check balances, and we add, create new exchanges and open up the orders. And this is all just that same application logic you can swap out for whatever you actually do. Same for cancel. Here we have a bunch of seemingly similar calls, and this is just like front-end tools that you can, it can build your front end easier, you can build other apps on top of it. So just different ways to reach the same data. I'm going to jump straight to deposit, because that's the first part of this interaction with other canisters we're going to talk about. So here you can see how we manage that deposit address that Tim mentioned earlier. So every single, every user of the DEX has their own sub-account that we use on the, so this is the DEX's ledger. And so then each user can call this get deposit address to get their specific sub-account that they need to interact with for the DEX to understand where ICP is coming from. And so I'll talk about ICP first. Our main deposit function just calls to either, depending on what we're interacting with. But if we're working with ICP, you can see we use that same account and we check that account to see if anything has been transferred already. And then here we actually make that call to the ledger canister. So here's the first sign of that asynchronous nature that we talked about. So this call is asynchronous, it's reaching out to another canister. And so because of that, and here's the one that actually transfers those funds. We pull them into our own default sub-account just to keep them all in one place. But you have to be very careful about these sorts of calls that can fail because of the asynchronous nature. So we have to be very careful about error checking and managing state so you don't roll back to a place where you can take advantage of something happening. Either you can double your tokens or whatever you want to do. And then for DIP20, here we have something similar. So here's where we create an interface to that DIP20 canister. And then again, we use this asynchronous, we call out to the canister a few times, and we make sure that if a call succeeds or not, we're in control of our state so that we can make sure we don't let anything slip through. Back up to withdrawal, that's the second half. This is just another implementation detail. So we've decided that if you pull your funds out, we just close your order so we don't have to worry about what you can still afford or anything. Or if you partially pull your funds out, we don't have to worry about any of that. So this is just a piece of logic that can be extended, but isn't actually important to what's going on here. We also just jump to these two functions. And here I want to show again that we're interacting with the ledger. And here's a good example of this rollback. So first we see if the book can pull a balance out of it. And then we make the call to the ledger. But because this can fail and because of the asynchronous nature, we don't want to roll back to a state where we've already removed the tokens before we go back to the user. So we check to see the result of that call and put the tokens back on the account if a user has, if a transfer didn't actually go through. And so we do the same thing here. We use this interface. We make a few calls. We remove the tokens, but depending on if the actual asynchronous call succeeds, we add these tokens back. We have a few more of these just generic functions. Here's a good example of, we use a query function here because balances aren't, just checking your balance shouldn't be super security related, so this can be fast. Most other calls are updates just so that they persist and are more secure than these query calls. But if you're just trying to write a front end that displays the balances, you can just use a query call, and the same for all of these. So there's just one last thing that I want to point out. We have a few of these here at the very end. We have a few of these functions that we've left in that, again, are really good for testing, but you definitely don't want to leave in production. So here it's just a credit that the owner of the controller of the canister can just credit whatever they want, whatever user, however many balance they would like. And this is, again, really useful for testing, but not something you want to leave in production. And the same for clear. So you just want to make sure that if you do use a template like this to start something you're working on, just make sure you remove testing things like this so that, yeah, just so it's safe. Even if no one's going to be in control of the canister, you just want to make sure that you don't leave stuff like this. And then here we are again at those, again, the upgrades. We don't want to leave this in production, but it's very helpful for testing. So that concludes our dive into the code. And there's just a few other things that I want to talk about. So I mentioned before, but query calls for speed and update calls for anything else secure. So you can even mix and match these where you can have the same information come from both calls, but use query calls if you need to have a fast reload on the front end, but use update calls if you need a more secure response. Managing rollback safely because the IC is asynchronous. So this is where we were checking the results of asynchronous calls and making sure that our the state of the canister is safe no matter what happens. And then back to what we talked about. So you want to keep the actual interactions with other canisters as simple as possible. So this is why we sort of broke it out to just those. There's really just 4 calls here that interact with other canisters, and everything else is just logic built around that. And this just helps you stay in control of, like, it both helps with the asynchronous nature, but also just the security of making sure that you can check your interactions and that those are all safe, and build everything else around it. And with that, we'll back up to questions. Thank you.
Yes, we do have some questions. So Eero, you also can check the chat room. So question from mcl.ic asked, how to import error type on TS front end? If there's not type of error in TS, it will be hard to parse on a to string and print, or we have to manually define error type again in TS. 1 second. Can you see the
yeah, I'm
number 1?
I'm not sure I fully understand. I do believe that our front end code can use the same or maybe the similar error structures, and we can just, it works out all the way through. I think that's what the question is. So I think we've just implemented the same error structures, and then it can be interpreted correctly from the agent that we use to make the calls.
Yeah, I guess there are some candid TypeScript utilities around. So I would suggest you to have a look at this. Maybe this fits your idea for the error handling. Okay, next question.
Okay, and also the Eero, you can check the Q&A function that we have. Frankie asks 3 different questions, and also Tim.
Yeah, we're from DFINITY Foundation.
He's asking how to make sure the deposit security and how to solve the scalable problem and demo from DFINITY official or psychedelic.
How to make sure the deposit security. You would have to be like more concrete in this question, because like as we explained the mechanism, and basically because it's like you basically trust the security of the IC that these tokens are there correctly. Like if you don't have like any logical bugs in the canister code. It's like tamper-proof, the canisters, by like design of the IC consensus and everything. Scalability, yeah, you have, for example, you have the canisters that can scale. So maybe, I don't know, error. So there are some parts that, for example, you can use query calls for. If you're not like 100%, it's not that important that it's like a secure call. So maybe there are some parts where you display certain information that it's not 100%, has to be 100% secure. Another thing is, for example, what you can imagine is that you have like different canisters for different maybe pairs. Maybe you have different, you can basically split the DEX if you want to have actual scalability. If you have like a very popular trading pair. Yeah, I think that answers Frankie's questions.
And then the next question we have is, why use principal ID, not to use account ID to host tokens? Do users need to know which can hold ICP and which can hold tokens?
So like account ID is something that's specific to the ledger. So that's why you need both. So if you want to interact with ICP, you need to use the account ID. Yeah, and usually you use, for other tokens, you use the principal ID.
Yeah, I think this also answers a question from Tim asking the difference between account ID and principal ID. So the next question we have is,
I can send you a useful link. Yeah, go on.
Yeah, next question we have is, besides transfer and read balance, what else can a canister manipulate ICP?
I think this might be the extent of the current interface that's exposed, is just making transfers between sub accounts, which handles all accounts, and checking balance. We had a question earlier about whether more advanced interactions are available through governance or anything like that, and I think that we do have some of that available, but I think right now that as far as the ledger goes, it's mostly just transferring and reading balance.
Thank you. Do you have any more questions? So this workshop lasts for 1 hour, and if you guys have any questions, please take this opportunity and feel free to ask Eero and Tim.
Okay.
We have another question from Tim. Yeah.
Why don't we use account ID? I can't. If you read the forum post, and just the account ID is basically just principal with sub account. This has to do with basically how the ledger was designed internally, and like for like DIP, for example the ERC20 DIP20 standard, they decided to just use your principal ID to interact with tokens. But you could imagine like using, like creating a token standard, but that mimics more the ledger. But that's just how it's just it's not given that you have to do it with a principal ID interaction with tokens. So it's just like some standards.
Thank you. And do we have any more questions from the audience based on today's topic to build an DeFi use case? Okay, so one of the audience asked, could you share the repo link?
Yeah. Yes,
sure.
Yeah, then it's in the subfolder Motoko DeFi. As mentioned by Eero, we have a Rust and a Motoko implementation.
And also we have another question from top list, that what is the right way to mint my tokens based on an ICP transfer?
Yeah, I did. I guess the first thing is like it mentioned like it depends on like your architecture that you have, because for minting you basically would need to be the owner in some kind of the token, of the Canister token. Then you can basically mint new tokens. What you maybe could do else is like you just basically have all the tokens in an account you control, and then you can just move from the account you control, but you don't mint basically new tokens. So minting is basically you add new tokens to the existing supply.
Okay, thank you. And do we have any more questions? And you can choose to type in the chat room. You can also raise your hand or in the okay. So one question asks that, what is the limitation of memory of Canister?
Yeah, I guess the limit is around a little, it's less than 4 gigabytes per canister that you can store. It's because we use WASM, and WASM is, if I know correctly, it's 32 bits, and with 32 bits you can only address more or less 4 gigabytes. That's why you're limited to more or less 4 gigabytes of state at the moment. But there is like an internal initiative going on to like look at how we could remove this limitation.
Thank you. We have a couple minutes left, and for those who have any questions, do not be shy. Okay, we have one question from the Q&A. So it's from Frankie again to add on more on the question he raised before. So users' deposits actually held by DEX itself, just like Binance hold the assets. So we have to trust Ledger, but for DIP token, is security rely on the DIP20 token canister?
Yeah, so as he correctly stated, so like our design follows more what you would know of, like for example with Binance. So you have like the central thing, the DEX that controls, and this also makes like the use of the IC, because we have like really scalable canisters that can hold state, and therefore like this is possible to do. So yes, you would, so you have to trust the DEX canister, but you kind of have to anyway if you want to transfer. Yeah. And so we have to trust the Ledger. So Ledger is like ICP itself, so I guess you can trust it. And for DIP token, the security relies on the DIP token canisters. Yeah, so if there is an exploit in the DIP20 token canisters, like yes, you have an issue.
Okay, thank you, Tim. So do we have any more questions? And also for also that today's workshop is recorded, and we'll put them on the YouTube channel, so you can also check the video later on. Okay. I think we might miss one question that I forgot if we asked this or not, answer this or not, is what is the right way to mint my tokens based on ICP transfer? Did we answer that one? Oh,
yeah, I briefly mentioned it. Yeah, I would have to go into more detail about what he actually wants to do to give like a more concrete answer to this question.
Okay, got it. So for public, you ask this question, and if you want to get more deep answer from Tim, you can just elaborate more about your question. And for the rest of the audience, and if you have any questions, just feel free to type your questions in the chat room or raise your hand or put your questions in the Q&A section. For those you came later, that you can check our video on YouTube, I think in a couple of days.
There's another question.
Yes, we have one more question. Yes. So is there any DeFi solution to not hold tokens like AMM on IC?
Yeah, as mentioned, like there are, it's just that this is an example. So this is just a design we came up with because we think it kind of highlights like some cool ideas that you can develop on the IC. But as mentioned, like, using AMM is certainly possible, and you can go, like, if you want to implement something like this, yeah, I guess it should be possible. It just you need to, as mentioned, you need to be careful with certain parts of the logic. And as I explained with the Uniswep example, like the implementation is not one-to-one translatable. Yeah.
Yeah,
Okay, thank you.
Just to, sorry, follow up on that. Our implementation is not the only implementation, but I hope that the some of the fundamentals we covered can be used in other implementations. So just interacting with these other canisters is the important part. And once you can do that, you really can build whatever you'd like on top of this. It doesn't have to be the same structure that we just demonstrated today.
Thank you. And yes, we have another question that can I have access to ICP transfer records within a canister?
I don't think that right now this is possible or exposed. I can't say if it will be in the future, but part of this is why we have this other design to track provenance through these sub accounts. And I think this is pretty standard too, to create like specific deposit accounts per user and track transfers that way.
Okay, thank you, Eero. And we have 5 more minutes, and cherish this 5 minutes and just ask questions you have. We'll wait 2 more minutes to see if that you have any more questions. Okay, when does SNS release?
Yeah, I don't want to put like any other engineering team, so I will not comment on the SNS release. It's just that it's actively being worked on. Yeah,
we would like to encourage you ask questions related to the DeFi use case. Okay, and I think if you guys have no further questions, that'll be the end of our workshop today. And like I mentioned, you can check today's workshop. Oh, we got one question. Okay, so we have one question from Frankie. So he asked, and I found it's quite difficult to pronounce. So
yeah, okay. Yeah, that's certainly true. And it's also about, like, if you ask yourself, like, why are you using AMM models? It's a very efficient. It's because you don't have to store much state on chain. So that's why, like, on Ethereum, like, they use these AMM models. But but yeah, I would actually have to think more about like how you could implement the AMM on the IC. I guess if you come up with some good ideas, it should be possible, I think.
Thank you, Tim. So I think that was our last question, and we have 3 minutes. So if you guys don't have further questions, we might wrap up for today's workshop. Okay. So I think that will be today's workshop. Thank you so much for your joining, and thank you so much for Tim and Eero for this wonderful time with us. And next week we are talking about build a DAO, and you can also check today's video on YouTube. Thank you so much for all your time, and looking forward to see you next week. Thank you, Eero, and thank you, Tim. Bye.